chemical properties of aryl halides. See, in the chemical properties, you will be seeing the reactions of the haloarenes or the alkyl halides. Then the most important category of the reactions in this is, these are the nucleophilic substitution reactions. The CSN reactions, which we have seen already, are the characteristic reactions of the alkyl halides. Now we have to see how the aryl halides responds to these reactions. Now first, the aryl halides are extremely less reactive towards nucleophilic substitutions. So they hardly show any nucleophilic substitution reactions. In spite of being polar, they have a very, very less ability or potential of showing the nucleophilic substitution reactions. What is the reason of this? They are, first of all, very less reactive towards nucleophilic, or we can write it SN reactions. Why? It is because, see, there are 4-5 reasons for this. The first is that in aryl halides, the halogen group shows plus R effect. Now it is like this, like if we have this chlorobenzene, the double bond shifts to ortho position, then it shifts to para position, then it shifts to again ortho position, and then it moves here, and then we acquire this type of resonating structure. Now what we find is, due to this plus R effect, the halogen and the carbon bond, that is one most important thing to notice, having a partial double bond character. So due to partial double bond character of CX bond, SN reactions becomes difficult. The reason being, it's very difficult to break 1.5 bond or a partial double bond, and it's much easier to break a single bond, whereas in alkyl halides we always have a single bond. That's the first reason, major reason of this the less reactivity towards the nucleophilic substitutions. The second is, which is again is very related to this one, that the carbon atom having the chlorine in this haloarenes is sp2 hybridized. Now, since it is sp2 hybridized, what happens is this carbon is more electronegative than the sp3 carbon. Therefore, the difference of the electronegativity between the carbon of this and the chlorine or the halogen is less. What we find is, that means, I can rub out this one. The second reason is that the CX bond in aryl halides is less polar than CX bond in alkyl halides. Why is it so? Because the carbon in this is sp2 hybridized, whereas carbon in the alkyl halides is sp3 hybridized. So less polar, shorter bond length due to partial double bond makes it this one less polar, plus sp2 hybridized carbon, and that is why lesser nucleophilic substitutions. There is one more reason. The arene carbocation, which we assume if formed, it is like this. This is unstable if it is formed. So this arene carbocation formed will be very unstable. That's another one of the reasons because of which what we find is that we have lesser reactivity toward nucleophilic substitutions. Second is repulsions of phenyl group or benzene ring, because benzene ring has a high electron density. Therefore, negatively charged nucleophile will always be repelled by this benzene ring or the arene phenyl group. So what we find is, again, this is phenyl group, or we can say benzene ring. That is why, due to these repulsions, what we find is, again, they have a lesser reactivity towards nucleophilic substitution. So all these reasons together contributes that the aryl halides are having very less tendency of nucleophilics, showing nucleophilic substitutions reactions. Now, what we have to see is, but yes, aryl halides under extreme conditions shows nucleophilic substitution reactions. So what we write is aryl halides under extreme conditions shows nucleophilic substitution reactions. Like, let me give an example. When chlorobenzene is treated with NaOH at 350 degrees Celsius, 300 atmospheric pressure, what we get is sodium phenoxide. This sodium phenoxide on reaction with dilute HCl gives us what? Phenol. So this is a very simple replacement or substitution of the chlorine by the OH group, and this leads to the formation of phenol from chlorobenzene. This is called Dawes process, and it's the best example, one of the best examples of what showing that the aryl halides under extreme conditions shows nucleophilic substitution reactions, and the extreme conditions applied are in the form of high temperature and high pressure. Now what we need to know is how or why, the most important thing, that the aryl halides are able to show nucleophilic substitution reaction under extreme conditions. The answer is because the CX bond, of course, is highly still polar. This bond is polar, and the minus I effect of the halogens in these aryl halides is more powerful than their plus R effect. So their minus I sense is more powerful than the plus R effect. What we find is the polarity is still very strong, and that is why under extreme conditions, yes, nucleophile is able to attack on this electron deficient carbon. That's the most important thing to note, and that is why the nucleophilic substitution, yes, takes place, but under extreme conditions. Now again, very interesting thing is notice in these aryl halides that the conditions of nucleophilic substitution reactions becomes much more easier the moment we have electron withdrawing groups like nitro group at ortho and para positions on the aryl halides. Like in this case, we have a nitro group attached to the para position in the chlorobenzene, and it's an example of a para nitrochlorobenzene. Now when it is subjected to NaOH and only at 170 degrees Celsius, no extra pressure, and then dilute HCl, what we get is Cl is being replaced by the OH, and we get what? The compound formed is para nitrophenol. See, in the original reaction, the same reaction was carried out at 350 degrees Celsius and 300 atmospheric pressure. Now the moment we have introduced just only one nitro group, the temperature condition has been reduced to almost half, and no pressure, extra pressure, and easily the nucleophilic substitution reaction takes place. Another interesting thing, if we have two such groups at ortho and para positions, like it is, what we can write is 2,4 dinitrochlorobenzene, the temperature required for the reaction of this nucleophilic substitution is getting reduced to only 95 degrees Celsius. And then with dilute HCl, we get what we get is 2,4-dinitrophenol. This is 2,4-dinitrophenol. So that's most interesting. And what we find is, if we have three such groups, electron withdrawing groups, even warm water is easily able to replace the Cl by an OH group, and what we get is the compound formed is called 2,4,6 trinitrophenol, which is also called picric acid. So see how the conditions for the nucleophilic substitution reactions has become so much favorable. What is the reason is? The reason is, let me explain it to you with the help of those resonating structures. The reason is because if suppose we are having a nitro group like this at ortho position, these are the lone pairs, what happens is nitro group shows minus R effect. Now due to minus R effect, what happens is positive charge is created on the benzene ring. Now due to this positive charge which is created on the benzene ring, if the electron withdrawing group is at ortho position, the positive charge falls on the carbon atom which is having the chlorine or a halogen. As a result, the nucleophilic attack becomes much easier to take place, and that is why it is able to replace this chloride ion. And that is why the moment we have one nitro group or a 2 or 3 at ortho and para positions, the nucleophilic substitution reaction becomes much and more easier. Now let us see if the electron withdrawing group is at para position, how it is going to help the nucleophilic substitution reactions. Let us see this one. See, this nitro group as usual will be showing what? Minus R effect. Now due to this minus R effect, what we find is this, we will have a positive charge here, N, negative charge. What will happen is we have groups like this. This will shift here. So the next structure we have is this. Now again, the positive charge is on that carbon atom which is having what? The chlorine. So therefore, the nucleophilic substitution becomes much more easier. Now, therefore, if we have three such groups, it becomes much more easier. That is why even warm water is able to what? Replace the chlorine. Now, what we find is, if such groups are present at meta position, the electron withdrawing groups are present at meta position, they are not going to change the conditions of the nucleophilic substitution reaction. Yes, you need to put same extreme conditions. In spite of being the electron withdrawing group present on the aryl halides, it's not going to change the conditions for the reactions. The reason is, let me put it like this, like suppose we have this group at meta position. It will show its minus R effect, of course. Due to this, this benzene ring acquires a positive charge. Let me draw those resonating structures for you. This will move here. This will move here. So you have seen it from here, it will come on where? It will come on the left hand side here. It will be here. So what you find is like this positive charge has what? Has skipped the carbon which is having the halogen. This positive charge never falls in the carbon atom which is having halogen. Therefore, it has no impact on what really on making this conditions of the nucleophilic substitution reaction easier. Therefore, if we have such groups at meta positions, it's of no use. There is no use. It is not going to change the conditions which are required for the nucleophilic substitution reactions. The second most important category of the reactions of the haloarenes are the electrophilic substitution reactions. We know that they are the characteristic reactions of all the benzene derivatives. Now what you need to know is that when any halogen is attached to what? The benzene ring, it releases electrons towards what? Benzene ring, is responsible for introducing a negative charge on benzene ring. Therefore, and it increases electron density at ortho and para positions. It will shift here on this side, it is like this. So what you can see in this case is that in these 5 resonating structures, the halogen is donating electrons, so it is showing what? Plus R effect. And as a result, we have what? High electron density in ortho and para positions. So what we write is, yes, aryl halides are ortho-para directing. But what is most important to note again is that since the electronegativity of halogens is more than the carbon, they always withdraw electron towards themselves through minus I effect. But therefore what we write is, but their minus I is more powerful than their plus R. Therefore, they are regarded as ring deactivating groups, and therefore they need what? Extreme conditions or stronger conditions or more harsh conditions for electrophilic substitution reactions than the normal benzene what it requires. So this is what we have to always keep in the mind, that yes, they shows plus R effect, but they are still regarded as ring deactivating groups because their minus I is more powerful than their plus R. And as a result, we need to put certain harsh conditions for their electrophilic substitution reactions. Now let us see how these reactions takes place. The first of the category is your halogenation. What we can have is, suppose if we have a chlorobenzene, we react this with chlorine, we'll treat this with anhydrous aluminium chloride. What we get is ortho-para substituted products. One is this, other is this. This is called para dichlorobenzene, and this will be your major product, whereas ortho-dichlorobenzene will be your minor product, and along with this we get HCl. So that's the halogenation. Now let us see nitration. Now in nitration, we use as nitrating mixture. So when the chlorine is treated with nitric acid in presence of concentrated sulfuric acid, what we get is orthonitrochlorobenzene as well as para-nitrochlorobenzene. Of course, para will be the major product as usual due to symmetry, and your ortho will be the minor product. Along with this, we get water. So this is what is nitration, with the help of which we are able to introduce nitro group at ortho and para position, and both the products are formed. Of course, the para one is major. Now let us see sulfonation. Now in sulfonation, we introduces sulfonic group on aryl halides. For this, we treat them with sulfuric acid and we heat the mixture together. What we get is we get para chlorobenzene sulfonic acid, the para as the major product and ortho as the minor product along with water. So sulfonic group is introduced at ortho and para positions. Two products are formed. Of course, para one will be the major one because of the symmetry. Then the last in the list is of the electrophilic substitutions is your Friedel-Crafts reactions. In the Friedel-Crafts reactions, let us see first alkylation. In the alkylation, chlorobenzene is treated with methyl chloride in presence of anhydrous aluminium chloride, which gives us what? Orthochlorotoluene and parachlorotoluene plus HCl. Always, this is the major product, this is the minor product. And this is how we are able to introduce a methyl group on the benzene ring at ortho and para positions. And let us see the second one, second Friedel-Crafts reaction, which is called acylation. In acylation, let us take a specific example. We are doing acetylation. We are introducing acetyl group. So we react this with acetyl chloride in presence of anhydrous aluminium chloride. So what we get is ketonic group at ortho as well as at para positions. It's like this. And what we get is para-chloroacetophenone. And this is para-chloroacetophenone because without this chlorine, this compound is called acetophenone. And this one is your major product, and this one is your minor product. Along with this, we get, of course, HCl. So these are the four types of electrophilic substitution reactions we are having in this category. The next reaction of the aryl halides is the reaction with metals. In this, we have two reactions. The first one is Wurtz fatigue reaction. Yes, it's an extension of the same Wurtz reaction which we have done in case of alkyl halides. Now, what is this reaction is all about this? In this, when any alkyl halide like chlorobenzene is treated with alkyl halide in presence of sodium and of course dry ether, Both the alkyl halide, aryl halide combines with each other, and we get the combination of the two together like this, along with what? NaCl. So that's most interesting to note. If this is made twice, you will be getting this twice here, and we get a mixture of this. Like in this case, we are getting toluene. This type of reaction is called Wurtz fatigue reaction, in which the combination of the two, alkyl and aryl, is formed by the almost the same, in the same method as we were having the Wurtz reaction taking place. The next in the category is the very similar reaction called fatigue reaction. Now in this, only the Wurtz type of reaction is actually being carried out with aryl halides. When aryl halides are treated with sodium in presence of course, dry ether, two of their molecular species combines with each other, and what happens is we get diphenyl. So we get diphenyl and of course NaCl, twice of this. So what we find in this case is it's a very similar reaction to your Wurtz reaction. The only thing is this, in this case, we exclusively taking only one alkyl aryl halide, which when treated with sodium and dry ether becomes double of this, the two benzene groups attached to each other, and that's why the compound formed is called diphenyl, and we get the salt outside this.